我们开始上课了。好，那上礼拜我们把7.1这个点和小块都教完了，那我们接着要进入的是边缘和轮廓。那这部分的话比较多是复习上学期的，就是电脑视觉教的边缘侦测这样，所以会比较轻松一点。好，那首先定义什么是影像中的边缘。好，那第一个就是物体的边界，这很简单。那第二个是3D 前后关系的遮挡，这应该也蛮好想象的，就是两个东西如果有互相的前后关系的话，那它中间会有一条线去把它们分隔开来，这样。好，那第三个是阴影边界和折痕的边缘。那第四个的话是一堆物体，那它会组成比较长的曲线或轮廓。那我们直接看下一页的范例图哈。好，那这边的话是4个范例，白色的图是人工标出来的边缘，这样。那可以看到的是左上角这个标的蛮清楚的，就是连右上的这个树荫它都把边缘标出来。可是像如果是右边这个鳄鱼的话，就可以看到说左上呃，对，我少讲一个，就是线的粗细代表说有多少人在这个位置标记说它是边界，像这个特别粗的部分，就是很多人都在这边说它是边界这样。那如果是这种比较浅的话，比较浅、比较细的线的话，就代表说有人把它标出来，但是人数比较少。好，那如果是像右边这个鳄鱼这一张的话，就可以看到说，虽然鳄鱼，就是这张图片的主角被标出来它的边缘这样，但是像左上角这个树荫的部分，其实也应该会是边缘，但是就比较少人标。好，那边缘侦测的话，就是这边复习的就是上学期的东西。那我们上学期有讲过，就是在边缘的话，它会有一个比较快速的亮度变化。那比较快速的亮度变化的话，又要用到我们的梯度去找，毕竟梯度对于亮度的变化还是比较敏感的。好，那所以这边的话，式子也很简单，就是直接对影像做一阶的微分，或者是可以用上学期提过的SOBO 算子，就是用差分近似微分的计算方式，会比直接算微分快一些。好，那第二种方法就是为了弥补第一个方法的问题。第一个方法只算一阶微分的问题，就是说它会放大杂讯，比如说 SOHO 算子就会对杂讯特别敏感，这样。那所以这个第二种做法的话，就是先用高斯滤波器把杂讯移除掉。那把杂讯移除掉之后，再去算它的一阶微分，这样我们就可以找到说，在没有受杂讯影响的情况下，然后梯度变化又比较快的地方，大概是在哪边？那这些地方就很有可能会是边缘。好，那如果要再找更细一点的边缘的话，可以用这个LOG。那它的做法就是一样，先对图片做一个 用高斯滤波器对图片做一次平滑，这样把杂讯去掉之后，我们做2次的，就是做二阶微分这样。好，那为什么要做二阶微分？这边有个图，就是说一般来说边缘的话，它的亮度变化会呈现像这个样子，它会有一个很剧烈的变化。所以一阶微分它会在这个地方，它会有一个peak，就是它会有一个比较高的值或比较低的值这样。那如果做二阶微分的话，那这边这个一阶微分这边的这个高峰，它就会变成一个经过零的，它就会变成一个经过零的区域。那只要在这个区域设置2个 threshold，去判定说，它如果经过这个 threshold 的话，就代表说它是一个足够可靠的边缘的地方。好，那这边的话就是课本上的范例这样。B 跟 C 的话是用 Kenny 和这个我会念的边缘侦测器去找出来的。那E 跟 F 的话，第一个应该说这下面这3张的话是另外一个上学期没有教过的方法。那课本这边也是提到而已，就是呃它的目标是为了要找到它的目标是为了要在边缘检测上去做尺度的选择。那 D 跟 E 的话，D 是一阶的导数，一阶微分，那 E 是二阶微分这样。好，那再用二阶微分的极值间的距离，就是刚刚我们找到的这种极值间的距离，它会去扣掉，这样，嗯，那刚刚说到说这个是二阶微分嘛，那它会用二阶微分的极值间的距离去扣掉高斯滤波器的宽度，等于它会得到每一个边缘的模糊宽度，也就是说它会去评估说它在什么样的尺度下，就是这个尺度由高斯滤波器的宽度来决定，这样，它会在什么尺度下去可以侦测到这个边缘，这样，那最后侦测到的边缘就是可以兼顾不同解析度的边缘，就是 F 这一张图。好，那这边就是课本就提到而已。好，那这边的话有不同的方式找边缘的结果，应该说它在不同的情况下找边缘的结果。那第一行这个 BG 的话是亮度梯度，就是纯粹用亮度去寻找边缘这样。那如果是第二行这个 CG 的话，则是考虑进去颜色的梯度，就应该说它只考虑颜色梯度，用颜色梯度去寻找边缘。那第三行这边的话是用 texture，就是材质的梯度这样。好，那最后一行的话，应该说第四行这一行的话，则是组合上面这三种，就是上面这三种情况，它都去考虑，然后去做边缘侦测这样。那可以看到是组合的话，它的效果会比较好一些，但是还是比不过人工去标记。 快吧，先往下。好，那边缘的话就差不多到刚刚那边。那接着是线和消失点。OK，首先是线。为什么要侦测线？是因为人造的建筑物或者是总之就是人造世界充满直线。那侦测和配对这些直线，很多应用上都蛮有用的。那这一章就是在讲说要怎么用直线去fit 一个曲线。那取完直线之后，要怎么进一步得到消失点跟应用这样。好，那一般来说会有这两种方法，piecewise linear跟 B spline。那 B spline 的话，之前的学长有补充，等一下会稍微讲一下，都不会讲太多。那 piecewise 的话就是蛮简单的，就是说我们假设有一条曲线，就是这边跟红线有一点叠起来，应该应该还是看得到。这里有一个圆弧的曲线是黑色的，那它这个 piecewise linear 的做法就是用连续的近似曲线去逼近这个黑色的曲线，这样。好，那最后的结果会是像 A 这张图上的红色线，可以看到是由多个直线去组合成这个黑色曲线。好，那第一个方法的话，就是它会递回去寻找说，在这个直线中，在这个曲线中的最弯曲的部分。好，那可以看到说，等一下，太快了。可以看到说，我们直接看 B 这里好了，就是说一开始我们会去寻找两个就是曲线的两个端点，那最一开始就是这两边嘛。好，然后它会去递回的寻找说这个曲线的最弯曲的部分，就是这个第一次寻找到会是这个点，就是像右上角这张图一样，那它会找到最弯曲的部分。那它用这个最弯曲的部分跟原本的直线的两个端点去连起来，就会得到用两条直线去逼近的这个曲线。好，那一样就是递回在这两个绿色直线的片段中去寻找说弯曲点最大的部分，像是这里这一条直线的话就是这边，那它再把它跟两个端点连起来，那连起来的话就会变成两条直线去逼近这一区块的曲线。那左边也是一样，找到弯曲最大的地方，然后把它跟两个端点连起来，就会那最终结果就会得到说 A 这张图。好，那至于要找多少，就是看使用者他自己去界定这样。如果直线太长的话，它如果嫌直线太长的话，可以一直往下切。好，那第二个方法的话，就是补充的，不会考。好，那第二个方法的话，它是把曲线切成很多个区段，然后每一个曲线，就是每一个区段中会分别有几个点去来控制这个曲线，这样。好，那像是 P1 这个点，它就会用来控制这个曲线的这一段的形状。那 P2这个点就会用来控制第二段这边的这个形状，这样。好，那做法的话就是从一条直线，然后透过控制这两个，应该说透过控制这些点来决定，来逐渐的逼近呃你想要找到的曲线，这样。好，那像右边的话就是其中控制 P1 的一个范例，它把 P1 往左边拉一点， 可以看到，呃，这个区段被往左边拉，但是第二个区段就没有受到控制。那 B-spline 的好处就是它的灵活性会比较高一点。好，呃，那接下来我们用这个后夫变换来做直线的侦测。那这一页的话是范例，我们先跳过，看下一页。好，首先一般来说，直线的表示法会是用这个方式，y 等于 mx 加 b，这个应该就是大家都蛮熟悉的表示方法，这样。好，那在霍夫转换这边的话，它会改用另外一个表示法，它会用到 ρ 跟这个西塔。那这个地方的话，它们分别代表的是跟这条直线跟原点的距离，还有跟原点之间的角度。好，那在转换过后，它在 ρ 跟西塔的这个坐标系上的话，它会呈现的是一个点，就是这一条线经过转换之后变成另外一个坐标系上的一个小点，这样。好，那如果是一个点经过这个转换的话，它会变成是一条曲线，就是它在 Rosita 这个坐标系上，它会是一条曲线。那原因是因为一个点可以有很多条直线通过，对，那这个很多条的直线就会组成这个曲线这样。那呃，这些曲线就是代表说这个点分别经过的点是，分别经过的线会是它的角度跟距离会是什么？好，那所以如果在原本的图中有一条直线，那它上面我们取三个点的话，就是 A、B、C 这三个点。那经过转换，把 A、B、C 这三个点经过转换，它会得到三条曲线这样。那这三条曲线的交汇点就会是图片中的这一条直线的那个点这样。好，那霍夫转换的话，好，先看这个范例好了。好，那刚刚有提到会是用这个，这边变数稍微有点不一样，但都是用这个直线，跟原点的距离和角度去做转换那个它的坐标系这样。好，那总之先把 x y 转成呃这边这边反过来 x y 转成 r c 这样。好，行，那我们看这个点，那我们会发现说，它如果有一条直线，它是负45度的，那它的 d 这边这个表是说它在这些角度上，它的直线跟原点的距离是多少？那负45度这个点，这个角度，它的直线又经过的话，那它的直线会是0。那如果是0度的话，它的距离会是1这样。那45度、90度一样，就是把它的 b 就是跟原点的距离记录下来。好，然后我们接着用一个表去记录说每一个点应该说每一个角度跟距离它有几条线这样。好，像负45度、负0.707，给定这些在给定这5个点的情况下，它会产生的线是一条一条。 那最多条的话，就会是这个-45度跟0.707，它会通过最多个点这样。还有这个90度跟距离是一的情况，它会通过的点也是最多的，有3个点。好，那2个点的话，就是有45度跟0.707和0度跟一。好，那霍夫转换的话，它的做法其实跟刚刚这里就是差不多的。我们先用前面提到的，7.1提到的说，我们会去找特征点，然后我们用这些特征点去做这个霍夫转换之后，然后我们去用像这种呃投票的表格，然后我们去找出说在哪一条线上它的它的票数最多，那票数最多的越多的直线，它越可能是真实存在图像上面的直线。好，那总结一下它的步骤。那第一个是刚刚提到的那个投票的表格，这样。那先把它清零。好，那第二步的话是侦测边线。那侦测边线的话，其实就是用刚刚提到的说呃把前面把直线的表示方式从原本的 y 等于 mx 加 b 转成角度跟距离这样。好，那接着就是投票，根据我们侦测到的特征点，那它的曲线之间，到底有就是到底有几条线是得到的票数最高的？那如果是最高的话，就把它选出来。好，那第四步是 optionally 的，就是它可以重新把这些选到的直线拟合到组成直线的这些边线上，这样。好，那另外一个找线方法的话是 RenSec，它的方法一样是一种抽样迭代方法，就是它会执行很多次这样。那第一步是它会随机选择2个点，那这里的点就是跟刚刚提到的一样，是我们前面找到的特征点。那用这2个点去构成一条直线的假设，这样。然后第二步是测试说有多少其他的点会落在这个直线上。那第三步的话就是说找到呃有落在，总之这边就是第二步就是会去统计说这条直线上有多少个点会落在上面这样。那第三步就是找到足够多点落在线上的那一条线。那那些线足够多的那些线，就会是我们要找的线段。好，那 RunSec 最好的优点就是它可以把 outlier 去除掉。那这边看一下范例。 好，那这影片就可以看到说，他挑了好几组线出来，这样，然后他最后保留的会是这一条线，因为这条线上有最多的点落在上面。这想一下，好，那这边的话是我不太确定这个可不可以讲。那这个是以前学长补充的，那他是用郑文煌老师的人工智慧的课程的讲义这样。那它用来说明的是，在 image matching 上也可以用 RenSeq 去做训。那他要说的是，在 image matching 上也可以用 RenSeq 去做配对。好，那他的做法是，一下。那它的这边的做法会是先找到一条正确的线，就是左边会先找到一条正确的线，比如说绿色的这个箭头，绿色这个箭头，那它会跟其他同方向的粗黄色的箭头去做比较。那呃这边可以看到说粗黄色的方向它会是相同的，跟绿色箭头会是相同的方向。那细黄色的方向的话，它就会是 outlier，就是它的方向跟绿色箭头这个方向是不一样的。好，那他要找到最大共识，就是说他要找到一个线，那它的 inlier 有最多，inlier 就是出的黄色这个，这些线，就是它们具有同样的方向，这样。那呃，出的黄色线叫做 good correspondence，那黄色的话就是 bad correspondence。好，那要找到最大共识的话，可以用 RenSeq。那第一个原因是因为包含一些随机性。那但是它的话就是随机性有点太强。另外一个是只能找到足够好的解，但不保证可以找到最优解。所以这边可以结合前面提过的设计有效率的演算法，搜寻附近的点，像是 Tree Search 或者是 BFS 这样。那这边就微考各位可以去，有兴趣的话可以看一下下面这个论文这样。
好，那个我补充一下哈，现在在讲课的是第7章哈，林金恩哈，所以呢，大家如果觉得他讲的好的话呢，请大家那个到时候那个期末考之前的话投他一票哈。那我们的话呢，就是 Turn Project 的报告哈，5月4号哈，这是下礼拜一哈。要来那个报告那个你的分发的进度，那就应该要变成原来1页嘛，现在应该变成3页了哈。再来5月25号的话变成那个3页，然后呢5月15号的话变成5页，然后呢6月15号的时候就变成8页，我们就会投到 CVGIP 去哈。如果上了的话呢，那个我会帮你出一半的旅馆的费用和报名的费用哈。OK， 请你继续的。
那我们先看一下笑话。 这边是最大声的。看一下，
你有插那个线上去？应该插一年线的话，不是，它有一个一年线。
这边没有，这边就这个。
那这好像是新的，好无所谓的。这个是 HDMI 嘛，理论上应该就直接从那里走了。好，没关系，那就算。哎，是最大的。 5分钟可以好，继续来。我喜欢这个口齿写手，对。对，下礼拜一来的时候记得带电子档哦，因为当场我们要改那个电子档哦。OK。Word 的电子档，Word 的电子档。
那当我们找到线段后，我们就可以开始找消失点。那消失点的定义是在3维空间的平行线，但是在2维的视角下会交于相同的点消失，称为消失点。这样，那我觉得这边的图其实都看不太出来，就是像这边说是左边这个屋顶上下2条线，它会有应该是平行的，但是照片是从2维角度看起来会倾斜的。是有一点的，但我觉得不是很明显。所以我们看这条，这个好了。那这个铁轨的话，它是在2维的视角下，它最后会交于这一点。那这个点就是所谓的消失点。好，那要怎么求消失点？第一步就是先做消失点的位置假设。这边的话其实蛮暴力的，就是用任意取两条线，这样 MI 跟 MJ， 然后去算出它们的可能的消失点的位置 VIJ 这样。那这个 VIJ 就是我们要找的消失点的假设。那我们之后就是要去验证说这个 VIJ 到底会不会是消失点。好，那这边 VIJ 的话，因为是任意取2条直线来做配对，所以可能会有很多个 VIJ。那我们就是要挑出最可靠的 VIJ 这样。好，那第一个评估消失点假设的指标就是权重。那我们这边的话，公式就是说，我们用 VIJ 算对应的权重。那这边的公式是 VIJ 的弄乘上 Li 和 Lj。那 Li 和 Lj 是个变数。那这个变数的话，Li 分别和线段 i 的长度有关，Lj 则是跟线段 j 的长度有关。那这个设计可以降低2种状况的影响。第一个是共线段，就是它几乎重叠的话。那第二个是短的线段。那短的线段的话，它这边就会很小，所以它的权重就会比较小，那它就不会被调到这样。那第一个方法就是算权重。好，那第二个评估消失点假设的指标是面积。好，用线段 i 的2个端点 pi0 跟 pi1 和消失点 v 形成的面积这个 a。那面积 a 会是一个误差值，越小越好。越小的话，就代表说它跟这个 v 越接近是一条线。好，那如果这个线段是直接指向消失点的话，就可以得到说它这个 a 的面积会是0。那面积的公式就是下面这个 pi0 乘外积乘上 pi1，然后再乘上 v 这样。好，那用刚刚2个指标代入公式，会得到这个最小平方的估计的。那它其实是加权的面积和越小越好。它的误差总和就是加总所有估计的消失点。 跟真实消失点的差异。那目标是要调整预测消失点的位置，来最小化加权的面积和。好，那这边的话是公式的话就是 v 就是刚刚评估到的消失点，乘上这个 wi 就是刚刚算的权重，跟 ai 就是刚刚算的面积，按这个我们要评估的线段，去做线段的长度去做相乘，这样。好，那这边的话一样也是用 RenSec 去找线，就是随机挑线出来，那再去算这个 Epsilon 的公式，这样。好，那这边的话最后一个小节会是影像的分割。这边是范例，就是不同的分割的方法。那首先看第一个这个。第一个方法，它会先决定阈值，就是它先决定 threshold，那再持续合并满足这个阈值的领域。以这个范例来说，最左边的矩形一，它的话就是它的这一块，它都满足阈值，所以它会被分在同一块。那如果到了中间这个分段这个边缘的话，它就不满足阈值的话，它就会分到第二块这个2这一区这样。那在2这边去找，你会发现说它中间这个3，它的它的像素又不满足这个阈值，所以它就又会被分到下一块这样。那最终就是会被分成这个样子，它就会有3个区域。好，那下一个这个范例就是这张图。那如果用刚刚的方式，就是先转成灰阶，那再做阈值运算去逐步合并的话，它就会分割成像右边这样。那分割其实没有到很好，因为一是2个背景没有被隔开，像这边，它这个球员的手下面跟这边其实没有被分开嘛。那只看灰阶值的差异的话，只要强度变化稍微大一点，那就亮度的
在我们的电脑视觉数位影像处理领域，通通是亮度好，intensity。
那亮度的变化只要稍微大一点的话，就会被分到不同类，像是左下球员的屁股的这个泥沙就会被分到说跟这个球员是不同的分割这样。
而且它下面的这个手这里跟这一块的泥沙弄成同一块，
这个手这边跟背景被分成同一块这样。还有这个花纹，球衣上的花纹也会被分到不同块这样。
然后它的这个上面这个人的鞋垫，对，上面这个人的鞋子跟下面这个人的头盔2个，甚至于他的那个左手这3样东西通通连在一起的。
对，这个鞋子跟头还有他的手会被分到同一块这样。那这就是用亮度去分的一个缺点。那另一个方法是这个均值漂移，那它的做法是观察每一个像素的关联特征向量，像是颜色和位置的分布状况，然后在分布中找 cluster。那最简单的方法就是先把 RGB 转成使用 RGB 将每个像素映射到3维 RGB 空间中的一点，右边这里的范例图 B 是使用 LUV 的3维色彩空间。好，那这边是转 LUV， 我记得第1章还第2章好像有讲过 LUV 的转换，那就是先把图片的颜色转成 LUV。 那转成 LUV 后，投影到 LU 的这两个维度。好，那右边的 D 则是把集中的点做159次的均值漂移，得到各个像素的 cluster 的结果。那在 LU 的 cluster 的图中，可以用分布密度画出图一，就是这个有山峰跟有谷的这张图这样。那越高的地方，pixel 越密集。那峰值的话，这边有用红点标记。那均值漂移要怎么做？就是用分布密度来做漂移。同一座山上的点，像是这座山，它会沿着这个轨迹一路收到这个山峰处。我们看下一页的影片 demo 会比较清楚。那左边的 3D，它现在已经被收敛起来。那左边的 3D 坐标图是从各个点沿着轨迹渐渐收拢到山峰点。这边它已经前面有点跳太快了，各位可以回去看一下。那右边的 kernel density 的 estimation 的话，则是用 kernel 来做收敛，那会是一个比较快的方法。也就是说，你随便挑到一个点，那它用一个kernel， 就是它定义一个领域嘛，kernel 来做移动轨迹，然后往平均密度增加最多的方向持续移动。那沿着移动路径半径范围内的所有点，就是这个圆，都会被归类到同一个 cluster。那等到每一类都归类好后，合并 cluster 中心点之间距离小于阈值的 cluster， 那它不会有很多小块。好，那这堂第7章就到这边。
好，我们先休息一下。
好，先休息一下。
好。
好，那我趁现在快速讲一下我的研究，趁老师不在的时候。好，那我的研究主题是这样：Super Frame with Dynamic Vision Sensor。好，那我们要做的其实是这个 Video Frame Interpolation。那 VFI 就是说给定两张 RGB 的 frame 当做输入，那计算出这两张 RGB frame 中间可能的 frame 这样。那它的应用的话，就是第一个是 slow motion，第二个是增加 FPS。这个有在玩游戏的应该都蛮清楚的。好，那讲一下什么是 DBS。DBS 是一种低延迟、低耗电的 sensor。那它记录的是两个，就是它记录的会是亮度的变化。那它的特性的话是它的 FPS 会比 RGB 高很多。那实际上是大部分的 DBS 都没有 FPS 的概念，就是它就是一旦亮度超过了一个他们设定的亮度变化超过了他们设定的 threshold，他们在那个像素就会产生一个事件。那这个事件可能是变亮，可能是变暗，那就是看亮度是怎么变化。那它也被称为叫做事件基础相机。好，那这边的话是一个范例，直接看影片。哎，你怎么不能用？ 好，那这些就是实际上 DBS 常见 DBS 会呈现出来的状况。那它这些白点通常都是每个像素它都会在不同的时间戳下产生的事件，这样。好，那我这边的话，就是厂商那边提供的 DBS 跟前面提到的市面上的常见的 DBS 不太一样。那厂商的 DBS 它的做法是用相机在一个时间段，一个很小、很接近的时间段内，快速拍2张照片之后相减，得到一个亮度的亮度图这样。好，那为了要训练，还有因为一些物理上的原因，我们需要去做 simulator。那这个 simulator 其实做法很简单，就是我们用240 FPS 的 RGB 相机去拍一段影片，然后我们把相邻的2个 RGB 的 frame 去转成灰阶之后，直接相减，就是用 I0减掉 I1这样。然后定义一个 ratio，那这边的话是用正负30，那只要这个相减过后的结果，这个 diff 它的在它在每个像素只要超过30的话，那我们就把它定义为它会变暗。那为什么大于30是变暗？是因为我们是用 I0减掉 I1，也就是前一个 frame 减掉后一个 frame。好，那如果是小于负30，就会变成就是变暗变亮这样。好，那其他的在30跟负30之间的话，就当做它没有产生任何的事件。所以240 FPS 的话，就是1秒可以产生239个事件的 frame 的。好，那这个 timelapse 是我们主要的参考的方法，他们的主要目标是要混合 warping base。warping base 就是说，我们先去算出2个 RGB frame 之间的亮度，之间的光流，然后我们再用这个光流去 warp 其中的一张，可能是 I0，可能是 I1，然后去 warp 到我们要的那个时间段的 frame。那还有 synthesis space， 那 synthesis space 的话，就是说，这里就是我们直接提供 I0跟 I1，还有这2个 frame 之间的事件，就是刚刚提到的 DBS 的资料，然后用一个模型去直接算出说这个我们要的时间戳的 frame 它可能是长什么样子。简单说就是直接生成了。好，那这边的话，他们有另外再加一个 refine 的 module。那 refine 的 module 就是要去对前面算出来的光流去做一个精炼。那它精炼的话，他们的做法其实蛮特别的，就是他们有发现说，刚刚提到的直接生成的那个 synthesis 的 module，结果在这边。他们在大部分的情况下，就是比 warping 的 module 还要好一些，就是他们大部分情况下都很好，在少部分情况会变得很差这样。那所以他们用 working 的结果和 synthesis 的结果拿来算残差的光流，然后再去对 working 的结果去做一次变形的，去做一次 work 这样。那这就是他们的 refine 的 module。好，那最后的话，他们会用一个attention 的 module 去把前面算出来的结果去做混合，这样。那就是 synthesis 跟 refine 的 working，然后去混合出最后我们要的结果。那下面这个图是呃这张这张图中有哪一个部分是用 synthesis，哪个部分是用 working 的？好，那这边有提到说 synthesis 的话，它的结果很不错，但是它在一些部分会蛮糟的，也就是说，这边是指说它在纹理比较复杂的部分，像是这个人脸，它的结果跟 ground truth，就是差蛮多的，有一个蛮大的变形，像这个眉毛这里就有一些变化这样。但是在这个光的变化亮度变化比较不规律的情况下，反而 synthesis 的结果会比较好，所以他们就是要，所以这个模型的目的就是要混合说模品的好处，就是在纹理复杂的地方，它可以得到好的结果，跟 synthesis 的好处可以处理亮度不规则的地方。那想要把它们的好处都混合起来，这样。好，那所有的 module 都是用这个 Hourglass 的 network。那我们的做法其实很简单，就是直接用这个 Timeless 提供的权重，然后我们在每一个 module，就是应该说每一个 layer 后面都加上一个1×1的 adapter。那用这个 adapter 去学习说前面提到的那种常见的 DBS，因为 Timeless 就是用那种不就是用前面提到看过的那些影片的那种 DBS，然后去学习它跟我们厂商之间的 DBS 之间的 domain gap。那结果是这是在厂商那边收集的资料上做推论后得到的结果，可以发现说它的 PSNR 在学习之前跟学习之后得到的进步是蛮多的，这样。好，那这边的话，我的方法就直接写在这，各位就自己回去看吧。这个我尽量写很少的。好，那我的 reference，OK，那我就讲到这边，换下一章。
喂，线上有声音吗？OK，好就可以。Okay. So hello everyone, my name is Valencia, or you can call me Luo Feiying. So today's lecture will be chapter 8, which is the image alignment and stitching. So to understand the idea of what this image alignment and stitching about, we can actually start by to see this example. So in the example A, you see this is a geometric alignment of 2D images for the stitching. So if you notice, there are like 4 images in here that being stitched together into one single images. But before it being stitched, it need to be precise by the alignment that using the geometric alignment. But how about for the figure B? So for the image B, this is a spherical panorama, and I'm pretty sure overall people in here know what this panorama is. So in this image example, there are 54 photographs that being constructed as a one single spherical panorama. Then how about this example? So in this example, if you notice, there are like 5 images, but this is an unordered set of collection images. And these 5 images is being assembled together into one single multi-image panorama. So from this, we can actually conclude that this chapter gonna discuss and cover about the technique on how to stitch the image, how to precise them using the alignment, and any methods of blending. So in this thing, we're gonna cover 4 sections, being divided into 4 sections. So 8.1 is the pairwise alignment, where we're gonna discuss about the feature matching using the ransack and least square. And for 8.2 is about the image stitching, the homography, and the rotational panorama. And for 8.3 is about the global alignment. So in here, we only gonna focus, in this chapter, gonna only focus on the bundle adjustment. And for 8.4 is about the compositing. So in here, we're gonna discuss about how this sim selection works and what is the methods of blending, which is Poisson and depletion. Okay, so let's directly start from 8.1, which is the pairwise alignment. So in here, feature-based alignment is the problem of estimating the motion between 2 or more sets of 2D or 3D points. But for this section, we only gonna discuss about the global parametric transformation, such as the basic 2D planar transformation. So in this graph, this is the common motion model that gonna be used in this chapter to be discussed. So from the very left to the very right is from the very simple to more complex or powerful the model is. So let's take from the translation. This is the most simple motion model. So this is only involve the displacement of x and y. But for the Euclidean, we're gonna add rotation. And for the similarity, we're gonna include like the scaling. Then how about for affine and projective? In here, we're gonna start to introduce deformation. Then if both of them use deformation, then what is the difference about affine and projective? In affine, we only gonna preserve about the parallelism. But for the projective, we're gonna change about the parallelism, the length, and the scale. So it depends on what kind of motions that your image is. That's why we're gonna choose like what kind of motion model will be corresponding in that kind of situation. So then the question is why we need pairwise alignment. So the goal is to estimate the geometric transformation between 2 images, because by matching them like one point in one images with another point in another images. And to do this, we have 2 approaches. So first is the feature-based, and the second one is the direct pixel-based. So I make it blur because in this chapter, we're not gonna discuss about the direct pixel-based, but this is like using the gradient descent to do that. Then how about for feature-based? Feature-based is the most important because when the structure is unknown, we're gonna rely or depends on the method called ransack to handle our outliers so we can get the inliers. So in here, as we want to remember the goal is to estimate the geometric transformation, right? So in here, we need to find the optimal P to do this. So how to do this is that to minimize the error, like this function, which is the minimize the sum of the square error of Ri. So in here, we need like this fxip and minus xi shift. So what is this? This is the predicted position, like our estimate position. And this one is our actual position. So we want to try to minimize this so it can make it more the point more closer to each other so we can get the optimal parameter P. Then why optimal parameter P is important in this part? Because the transformation function depends on the P. So how we actually to get this P? But this we'll discuss later in the slides. So next one is about this one. Because many motion model that we mentioned earlier, for example, like translation, similarity, affine, they have a linear relationship between their motion and their parameter P. So in this case, we cannot just do like this part, least square, because now we need to introduce the linear like regression, or we call it as ELLS, which is the linear least square. So in here, we define the J is the Jacobian. So this is the partial derivative of our transformation F with respect of the parameter P. So in here, you can see like in this equation, it's also almost similar like this part, right? But the only difference is this delta xi. So what is this delta xi? This is the actual measure displacement or like the distance between the matching point. And for the GXIP is still the same. It's our predicted position. And the goal is also the same. We want to minimize this function to get the optimal P. So by setting this up like as a linear problem, we can find the exact value for the parameter P. Like for example, 6 parameters for affine and 4 for the similarity. However, just now we keep talking like we need to find optimal parameter P, right? But how actually mathematically we solve this P? So if you actually take the function in this part and we try to derive it into the more equation. So from this equation, we can rewrite the inner product. For example, like we can identify this form factor becoming like factor multiplied by factor transpose. So we can use this GXIP minus delta XI multiplied by its own transpose, and we can get this kind of equation. After we get this equation, we can also make it more simple to rewrite it by just substitute like A represent for this part, and B represent for this part, and C for this part. So now we can get the final product, which is, final form, the P transpose AP minus 2P transpose P plus C. So in here, to find the optimal parameters P, we need to put this P out from the form, right? So in this case, we need to find the point where the error is at the lowest. So it means we taking this first derivative of this function and setting it into 0. Because by this thing, we can solve the derivative. And now the entire complex can be more simplified as A, B equal to B. Where A is the same matrix for this one, and for the B is the same for this part. So now we got the equation AP equal to B. And also P is the parameter we want to find. So, however, up until now, our discussion, we only assume that our matching points are equally reliable. But in reality, the data is very shaky and perhaps like very blurry, right? So in this case, like the matching point is sometimes is reliable, but sometimes it's also unreliable. So how we handle this thing? To handle this thing, we just assign uncertainty weighting. So we assign like this variable Wi, which is the weight. So for the high confidence, we're gonna assign to get a height weight. But for the low confidence, like for example, noisy, we just assign with the get the low weight. So in here, as you see, it's actually also similar like this function, but the only difference is because we assign the weight. So that's why Wi in here. And if we also do the derivative, the calculation like before, we can also simplify the equation as this part. So yeah, by adding this matrix W, we can ensure that our final alignment is dominated by the most accurate data. So what is the application of the pairwise alignment? So one of the simplest application is the panography or panorama. So in here, because panography is like we stitch the images into one images, right? So in here, the images are shifted and also optionally like rotated and also scaled before the blending to becoming this one panorama. And the more detail will be discussed in later section. So the common motion model that for this doing this panography is pure translation, or we call it as translation with some small rotation or scale. So if we only consider like pure translation only, the basic idea is like to find the offset, this TJ. So in here, we take the feature point of TJ from its local image coordinate xij. And after that, we're gonna compare it with the result of this true global position xi. And overall, the goal is also the same. We want to minimize this kind of function, this total error function. So to match the global consensus of this xi as closely as possible. So since same feature like this E point that can might be observed across multiple different images, which is like defined as J. So it should technically have only one true position, and the true position is xi, which is the global coordinate system. However, in practice, the coordinate of the corresponding xij as this part in each image will contain some error. So we need the translation amount TJ for, and sorry, the translation amount of TJ is also unknown. So how to solve this is that we need to solve for the translation amounts of all the images and also the global coordinate of the every feature point. Okay, let's actually have a short break. Be quiet. Oh, sorry. ch7-8 觉
得还好。
还好吗？然后是满意还是很快？
我觉得维持这个速度应该差不多。
嗯，
维持这个速度应该 OK。
OK，所以不用。
你现在已经有分享哦，所以应该只要切到。
不要。对，就是这个哇。对啊。
可以了。
好，很好。
可是
这
取消。
这样，entire screen。可能是这样的。
怎么？加上来去。
没几个。好，那角色应该也是可以吧？
是你这样没办法切那边，这边可以跳出去。
嘿，可以吗？
哦，
好，感谢你哦。可以吗？
可以。
这边也是。OK。Okay, so let's continue to our this 8.1.3 iterative algorithm. So in here, why we need iterative algorithm. So just now we was discussing about least square and then linear least square. But although this is although the linear least square is like the simplest way that we can estimate the parameters, but the measurement and like some it's like unknown, like in reality. So it's often do not have like the simple linear relationship. So in this case, the problem becomes a non-linear least square or non-linear regression problem. So for example, consider the estimating of the rigid Euclidean 2D transformation, like this is translation plus rotation. So between the two sets of the points. So we try to represent like the transformation with the translation, which is defined with this matrix Tx, Ty, and for the rotation angle, which is the theta. So to minimize this nonlinear least square problem, we need this iterative algorithm to update the delta p. So how we update this thing? So in here, we will, so basically this is also the same like calculation with the before, but for now, we will just like changing like the xi, like the delta xi with the ri. So in here, we also, the goal is the same. We try to minimize this error function, the result. And it's also the same in here after you do the calculation like the previous slides that we do. We will got like this equation. And this part can be, is the same A matrix like before, like this one. But the only problem is on the B. So the B is different. In B, it's being defined like this. So yeah. So in here, it's also the same. Basically, this part is a Jacobian weighted sum of the residual factor that we want to minimize for the non-linear least square. And once we got the A and B from the calculation, we can use like the following equation to solve the delta P. But in many applications, if the system is converged successfully, so we can just set the lambda, this part, to becoming a 0. So now, is a robust least square or ransack. This is also being explained in the chapter 7 about the ransack. So why robustness is necessary? Because in real world data, there are like so many outliers and we try to handle it to get the inliers. So what is this outliers? It's because of the incorrect feature match, the moving object, and the points with the height noises. So the problem is, if we directly include this thing in like least square, then there will be a large error that can distort like the solution. So because of this, we need the robust technique. And one of the example of the robust technique is the ransack, random sample consensus. So how we do ransack? In the chapter 7 is also being explained how to do ransack, but I will try to explain again in here. So first is minimal sampling. So it's randomly select the k points. So, and then model estimation. In here, we try to compute the model parameters like the transformation P by using only those k points. And next is about the verification, the consensus, or like the scoring. So we try to test the model against all other points. So a point is inlier if its distance to the model is below the error of the threshold. And the thing is, in here, we want to keep the model with the highest inlier count, which is defined as C. And then we do the iteration. Sorry for the number in here, but basically this is 4 and 5. So in the iteration, we try to repeat S times. So like to maximize the probability of picking an outlier-free sample. And after that, we have the final refinement or the global refinement. So we use the best of the inliers found by perform a least square fit on the entire inlier group. So this is to average out any remaining noise and finalize the parameter. So now, because we do iterative S times right in here, then how much or how large S that we actually needed? So in here, because we need some reference data because most of the data are inliers. So you need to tell like the estimated probability of the inlier. So for example, if you have 70% of the data are correct, then the small p in here is 70. So this p is represent on how likely a data point belongs into inlier. So how about the big P? So big P is the probability of finding the correct model after running S types. So for example, if you have 0.95, it means that the final output of the model has 95% confidence that it's being correct. So the higher this big P is, the larger the S will be. Need to be. So because you look at this formula in here like this, 1 minus p into the power of k. So because of the probability of, because small p is the probability of selecting the inlier. So small p to the k means it's like probability of selecting k inliers. So and in here, you see like, okay, this is like taking 1 minus p to k represent like the probability of selecting the bad sample. So if the bad point is included in the model, then it will be incorrect. So by raising the power of this S, it actually, you have sample like S times and none of them are good. So, and then how about this big P? Then this is the probability that at least one sample is good. But if we actually subtract 1 minus p, then this is the corresponding of the wait in here. Okay, so this is the corresponding on how the bad product is. So now in this part, you actually see like the table. This is like the relationship between the k, the p, and the s. So you see if like the number is like this, then p and s will be like that. So now, because many computer vision applications do not require like aligning 2D features, but it actually rather aligning the 3D points. So in here, 3D transformation, where the motion parameters are linear, like for example, like the translation, the similarity, and affine, can be solved using just a general least square. But however, for example, like in the rigid motion, like a Euclidean, so it's gonna occurs more frequently and is often referred to the absolute orientation problem. So we can just like this part using a different technique, which this one. So did you still remember that in the very beginning I said that translation is displacement in x and y, and for the Euclidean is just adding the rotation. So now in here you see that we can estimate the translation, which is defined as the formula d equal to c shift subtract with rc. So this is to estimate the translation by c the difference between 2 points cloud of c and c shift. So next, we need to estimate the rotation between two sets of points, which is this point and this point. And a commonly used technique for this is the orthogonal Procute algorithm, which performs SVD on the correlation matrix. Then with this part, we can get the rotation matrix as defined as R equal UV transpose. Do you want short break? Or should I just next? Next. Okay, next. So now we go to 8.2, image stitching for homography and rotational. So why image stitching? So image stitching, basically image and stitching. So you stitch the image. However, in this image stitching, there's still like some problem because of the alignment on blending, because I mean like different fish, like different motion, ghosting and stuff. So in here, there's a key steps on doing the image stitching. So this is the first technique. First, we need to choose a mathematical model. So like what kind of type of 2D or 3D transformation that you need to use. And then we need to find the parameter relation between the images using the feature point or the direct pixel matching. And the third one, we're gonna do like aligning the images, but we need to choose the final compositing plane to warp the aligned images. And finally, in the compositing and blending, we just seamlessly stitch and blend the overlapping legend of the images. Then the question is why we need the motion model. So when we try to align multiple images, the problem is that how does a pixel coordinate of like X and Y in one image correspond to the coordinate in another images. So this correspondence can be viewed as transformation. And there are several types of 2D transformation. For example, like translation, similarity, affine, and homography. And if the situation allows, sometimes we also consider the 3D rotation, depends on how like the images we try to solve. So, but now in here, we're gonna focus more on the homography because this is one of the common example of the technique of planar scenes. So this is when the scene is planar or the camera is only rotates around its center. So it can be represented as the matrix 3 multiplied by 3 matrix. And it's gonna satisfying this kind of matrix. For the planar scenes, like for example, like a piece of paper or just like pure camera rotation, when the camera center is actually fixed and only like rotates like around its axis, so actually the camera is not moved, it's just around like the axis, then this thing we can just ignore the parallax. Then this model can be used to describe the transformation. And then how about 3D rotation model? So in this case, if the camera only rotates in place, like for example, no translation, then we can assume that the scene is at infinity and use a pure 3D rotation instead of like this homography or we call as planar scene, because with this will be fewer parameters and better stability. So to conclude, we choose the model based on how the capture condition is. And one of the application, simple image stitching application, is to stitch together number of the image scan that taken from the scanner. So for example, like if you have a large map or artwork that like too big, but you want to feed it into the scanner that is small, then we can actually scan it by overlapping like the parts. So this overlap should be large enough to ensure that all the feature is included. Then after we get all the feature from these overlapping points, then we can, this is called as feature detection. Then after and feature matching, then we can estimate the 2D rigid transformation to align the images. But there's still a problem with this thing, because if you actually can see the problem with the scene, if each image is aligned, then sequentially like just stack together, then this will accumulate it like the errors over the time. And in this case, we need the solution, which is the global alignment for consistency of global. This is gonna discuss in the section 8.3. And if the document is not perfect planar, for example, like the paper is wrinkled, so now the homography is not is inaccurate. Now we need more better solution, which is like more flexible alignment method that need to be required. And for panoramic stitching, the most common case is the pure camera rotation. So what is pure camera rotation? You only stand still, but you actually turn your camera. So you're in here, but you're basically your phone in here. So at a place like the Grand Canyon, the scene is like very far away. Like you see, it's very far. And so it can be treated as like infinity because you cannot see like in the very behind. And this means there is also no depth change because the distance is so far and the point is also don't shift in the space when you rotate. So we can just simplify this as a pure rotation. So what is pure rotation? It's just now like what I say, you are standing in here, but your camera is moving, and your camera moving, but you cannot move it like front and like back, okay? Because like you need to be stable like this. So in this case, if we actually do like that, then we can projecting from the different viewing angle onto the same plane. So, but if the traditional plane is used, then large field of view can cause distortion. So to solve this, we're gonna use the cylinder or sphere. Now this is the example of this one, the planar. So this diagram shows that the light rays coming from all direction, like this black line. And then we have the purple one is our camera center. So basically all the light rays is go through in here. And then this is our real camera sensor. And in this part, we got like one viewing angle over here. And this red one is the feature points. So if you want to turn this and stack them together into a one digital image that is big, then we need to take this feature point and align it together into in here. So the result is that if we have multiple images taken from different angles, now we can project it into one same plane from different angles. And this is called as mosaic projection plane. Okay, sorry, being cut. Then how about if you want 360-degree field of view? In this case, we're gonna use cylinder projecting image. Because with these different images that we got from 360-degree view, we can actually map it into a cylinder. So how we do this? So first step is the project the multiple images onto the cylinder, and then we blend them like this one. And then after that, you're gonna produce like the cylinder image, like this part. Then after we got like the cylinder image, we actually can unwrap them, become into a one plate. So it's called as a flat panorama. This is we'll discuss later how to do it in the next slide. So the thing is, from this problem, this method often have like some problem because of the gaps and some holes in the areas. Because in reality, you see there is an accumulated error. And after that, because small error is like each estimation is add up. So for example, that you actually estimate there is 30 degree, but it actually 29.1. So it's not match. And the result, there is a gap, like the blank space. Because suppose if you want to do a cylinder, it need to be loop like shoot like the end of the image need to be like match, like need to be meet together. So for example, if you have a small 0.9 error per photo result, then there will be like 10.8 mismatch after 12 frames. Then what is our goal? Our goal is to shooting a full circle, and the first and the last images need to be overlapped to perfectly close root. Then how we do this? How do we solve the gap closing? So first we detect the first and the last images that is do not align perfectly. And then we try to compute like the mismatch, like for example, extra 32 rotations or 9% of the focal length error. Then after we get this error, we can distribute this error across all the image parameter, or we just like adjust the focal frame. So the panorama can properly close into one loop. Okay, this is to make it more easy to understand. You can see this small example for intuition on how to do the gap closing. So like suppose we estimate that each step rotates like 30, but the true rotation is 29.1. So this is not line, right? So after 12 images, the accumulated error become like 12 multiplied by 30 minus 21, 29.1 is equal to 10.8. So now the last image no longer match the first one. So this leaves the gap of 10.8 gap. So to close this gap, we try to distribute the error evenly all the frames. So using this 10.8, we divide it by 12 frames, and now we got 0.9 per image with the correction. So after we do this adjustment, now the sequence can become consistent and perform like the perfect 360-degree loop. So I hope this intuition can help. So this is one of the application of the image stitching in the live sports broadcasting. Since it's a real-time like streaming, reducing the video compression and transmission data is important. And the main focus of the sport games is actually the player, right? It's not the background, it's not the audience, it's the player who play the football. So in this case, we can capture only the real-time motion of the players, and we can just reuse like the background from the same slightly different time frames. Because with this thing, we can reduce the data size because we can just overlay the player on on the same background instead of different background, different player. Then why we need to use cylindrical or spherical coordinate? So when the field view is like so large, planar projection causes distortion. So if we stitch these multiple images into like so many wide view, like for example, even like 360-degree panorama and map everything into one flat plane, then the larger the view you want, it will also more giving the larger or severe distortion at the edges. So to solve this, we use the cylindrical or spherical projection to reduce the distortion in the wide panorama. So to make it more easy to understand, like let's look this example. So there are 3 images, and this is the result if we just stitch it together into the planar. In here, we didn't perform the cylindrical projection, so as you can see, it looked distorted, right? This doesn't look good. But now, if we actually add the cylindrical projection, don't you think it looks better? So yeah, because of this, we want to use cylindrical and spherical coordinates. Then, how we can get the panorama from the cylindrical? So our image coordinate system in planar is x and y. But to use the cylindrical, we need to change it to theta and height. So which are the coordinates of the cylindrical coordinate system? So from x to y, we change to theta to h. Then the horizontal, so if your original image is in here, this f is the focal length, and from the camera center to your flat image plane. And this is theta is your angle, and x is actually your position of the horizontal image. So by using from this triangle, we can try to use trigonometry identity. We can get that the value of theta is equal to r tan x per focal length. Now we got the theta value for this one. Then how about to get the height? So to get the value of h on the cylinder, we need to see on the vertical pixels coordinate y on the original images. So first, find the distance from the camera center, this part. and then to the point X on the image plane in this part. And then in here, using the Pythagorean theorem, we can get like x squared plus focal length squared after we use the Pythagorean identity. Next, if we use the dissimilar also triangle, then we can take that the ratio of the height of the cylinder is the radius, that is the same ratio as the image h. So in this case, we can just give the equation as h equal to y per square root of the x squared plus f squared. So now we get the h. However, our goal is to make the flat plane from cylindrical. So now we only have the cylindrical images. So to make it flat, we need to unwrap it. So now it means that we need to change the theta h back to the xy. So we define it as x shift and y shift. So in here, as you see, we multiply the s scaling factor, and in here, s is equal to f because it will give less distortion as we assume that our cylinder radius is 1. So why we assume this thing? Because it means that the image we're stitching on the cylinder. So that's why the radius is 1. And now we can get x shift and y shift. It's basically the same like theta formula and height, but the only difference is we actually multiply with the scaling factor. And now we can get a digital flat images from our cylindrical projection. So focal length is the secret on how we project the image. As you see, it actually from these different images, you can see the difference, right? Like the left one is the original image, and the right shows like different focal length result. So in here is only one correct, and we need to find the correct focal length to project the image to the right position. So after projecting images onto the cylinder, the motion model becomes simple translation. Only x and y shift need to be estimated. So, however, if we want to capture like the sky above and also the ground, we cannot only use cylindrical projection because cylindrical projection is like only horizontal, so it will just look like this. So if you want to capture like the above and also like the ground, we need also the vertical projection. And in this case, to use the horizontal and vertical is using the spherical projection. So in here, the equation also similar like the cylindrical in this part, but the only problem changing in here is the f focal length. Yeah. Okay, short break. Ten-minute break.
然后我们刚刚说，我们真的要跟你们介绍，真的想让大家体会到的要懂抽象的，然后比较看那种，然后做懂到说，然后正常看比较高阶一点的方面，看到这道理，好的，还不错。感觉到有可能。你知道吗？但是我人生中很少见的两个词，我所知道的。到很抽象的一个完全不知道怎么办。我后来看后面看来你在你都当然这也不麻烦，但是如果你没有要改，那也要那也是对，不要自己包括到底看看你有方法，然后这套的道理，该会怎么样？应该会怎么样？有书啊，哦，然后那种我会怎么感觉？我会。哦，就是把我正在哦。 Okay, now presenting chapter 8 is Law Fei-Ying, Valencia law. Okay, so if you think she presents well, please vote for her before the final. Okay, go ahead.
Okay, so we continue our discussion into 8.3, global alignment, and using the bundle adjustment. So why we need global alignment? Because pairwise alignment is only optimized for images step by step. And this can produce like a good local alignment, but it's lack of the global consistency. So because of this, we need the global alignment to make all the images to consistent together. So in here, because multiple overlaps require global alignment, so we need to optimize all the parameters together. But before the global alignment, we need to get a good feature points and matching points. And in this case, we use the ransack first. So in this part, there's like images, and these points is the feature points that are found. And using the ransack, we can actually filter out and get like the inliers that is gonna be used. And using these inliers for the image stitching, we can get this result. But if you notice, this is not like smooth because there's like a difference in the as you see here in the middle. So this is because it's lack of the global consistency. And how to solve it? We use the bundle adjustment. So in bundle adjustment, we need to minimize the function of this part. This is considered like the errors of the corresponding features across all the overlapping images together. And the result, if we minimize this, then we can get the global consistent final result. But however, even after optimizing like the rotation and the focal length, there's still an issue, which is the ghosting or the blurring, or like the blurring. So this is because like the image is still not perfectly aligned, and some areas will have this ghosting and blurring. So because in the real scene, like there is a depth variation and camera translation, and not all the points can all align together with a single 2D transformation. So this is lead to the ghosting. And this could be caused like by different factors, like variety of factors. So this include like 3D parallax because of the failure to rotate the line's total point, and the scene motion, which is the ghosting because of the moving object like people, waving trees, and also another is lens issue, unmodeled radial distortion. And because of that, now we see this example. This example is the parallax removal. This is to solve like the problem of the ghosting and the blurring that we get. So how parallax removal actually works? If you actually see this first example, there are so many blurring like parallax because this is just stitching the images without undergoing any process. And for the part B, we do the single deghosting, and now we can get like more kind of better. And after that, we do in this part like multiple deghosting operation, and now the ghosting or like the Broglie effect is gone. So what kind of technique that can be used to remove the parallax? So there are three in here. 3D bundle adjustment. So in here, models camera translation and recovers the 3D structure. And the result, the scene is a single parallax-free viewpoint. However, it's expensive. And another one is local warping or mask batch. So this applies the localized 2D warps to overlapping segments. And another one is layering or composition. It separates the foreground background layers to handle the dynamic object of varying depth. But for this section, we're gonna only focus on the how 3D bundle adjustment work for the parallax removal. So how it works? Because of the 3D rigid model, multiple images, like this part, images, are captured. And using the corresponding projected points in this image, like as you can see, x1, x2, x3, and this relative motion between the camera and this parameter called as the bundle adjustment. And in simple term, we use the 3D bundle adjustment is to minimizing the reprojection error. So what is reprojection error? It refers to the square distance between like our feature point, as you can see here, and those with our predicted images, like the one that I just discussed in the section 1 about how to minimizing the error function. Okay. So now it's 8.4.
Yeah, I like joke. Yeah, joke is more important. Yeah, than text. This will be in our final examination. Yeah. I like next argument. Now is
How?
now is the value. The highest value. Yeah.
Okay.
Good. That's good. I like it.
Okay, so now we finally got into our last section, 8.4 compositing.
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 Yeah, compositing.
Okay, so it's a seam selection and the technique of blending, which is the Poisson and
That's French. This poisson.
Poisson.
Yeah, poisson. Yeah.
Poisson
Yeah,
and Laplacian blending.
Poisson actually means fish in French. Yeah.
So after matching all the input images like we discussed, like in the very previous slide, now we need to decide how to generate the very final stitch images. So this include by selecting the final composite surface such as composite.
Yeah, composite.
This includes selecting a final composite surface such as the plane, the cylinder, or the sphere. And we also need to select which pixel that gonna contribute to the final composite. So to how optimally blending this pixel and minimize the seams, the blurring, and the ghosting. And the first choice is to make is how to represent the final image. If only a few images are stitched together, one approach is to select one image as a reference and then warp the other images to the reference image coordinate system. But we sometimes use planar panoramic images. But for images that have a very large view, it will be difficult to maintain the planar, like what I stated before, because it will excessively gonna stretch the pixels near the image boundary and it gonna cause the distortion. So that's why for the large panorama stitching is typically done using the cylindrical or spherical projection as I introduced in earlier. Because real images may contain seams because of the exposure difference, and then the blur because of the matching errors, and ghosting because of the moving objects. So after pixels are projected onto the final composite surface, we need to decide how to blend them to produce a clean panorama. So in this case, to do that, we need a pixel selection. So how to do pixel selection? There are 4 common strategies: the feathering or center weighting, the p-norm or Voronoi, optimal seam, minimum energy seam, and deghosting or moving object handling. But for this part, we only gonna focus on the deghosting or the moving object handling. So there are 2 strategies to solve this deghosting. So we keep the object from one image and ignore the others to achieve no ghosting while keeping the subject. And to remove is to get an empty scene, like for example, we remove the tourist and then apply the per pixel median and percentile over time to eliminate the moving elements. And also because of the exposure sorry for the format. Because of the exposure differences and motion, we need to first perform exposure compensation, which is the local polynomial Alkin map, to reduce the base differences. And after that, we can apply the scene finding or deghosting for the best result. So for example, in this example, there is this called deghosting or moving object using the Photoshop photo merge of the remove ghost. So there are actually 6 images in here. So when the traffic is heavy, because the car is moving and maybe the people is walking, the remove causes can in this Photoshop can automatically select frame with the fewest or no cars to avoid semi-transparent vehicles. So the word semi-transparent means ghosting. So compare, and after that, compare the result with or without to check for the ghosting. Then how to do this? So first, we find the conflicts by warp all the images onto the same coordinate system and compute the pixel differences. And after that, we select which bus images they're gonna use. Because if a pixel differs different too much, it will likely have a motion. And that's why we need to choose the most consistent source of image. And after that, we create the mask, like in this, as you can see, there is a mask. We generate a mask for its images, and then we blend smoothly or like apply filtering or reflection blending to avoid the seams. And the final output, we combine all these masks to produce like the cost-free panorama as this thing. So although image stitching is usually used to composite photos with
Composite, yeah.
composite.
Yeah, composite.
So although image stitching is usually used to composite photos with overlapping parts, it can also use to composite scenes that have been shot like repeatedly, with the aim of optimizing the best composition and appearance for each element. And one of the example for this is called as a photo montage. So this is
This is also French photo montage.
photo montage.
Yeah, photo montage.
Yeah, photo montage.
Yeah, photo montage.
So this is the example. As you can see, there is this blue blue box, yellow box, red box, green box. So this is represent like different part that will be used in the second images. So in here, we choose like, because in this example, this is like a family photos, and they want only to choose like best expression from each person, and that's why they try to find from these 4 images what kind of things that I want to put in my final images. So using this multi-level like graph card, each of the pixel is assigned a label indicating like from which images it belongs. So for example, this one from here, this part is like from these images, and this part is from these images, and this part from these images. So after that, after we find the seam, then we can now minimizing all the function at the boundary, and this can help us to avoid the conflicts of like moving object, and we can also get like the output that we want with the best expression of the family. And after alignment, there is still overlaps that like because of the expressional differences. That's why we need blending, because like brightness, white balance difference, more misalignment like jagged edges, moving object like ghosting and double images can be solved using the blending, because by blending we can make the colors, the different brightness, edges can be more continuous and more smoothly or seamless. So this is like the example, like simple example of how the blending is. So the left side, which is the color red, and the right side is the blue one. So left side is like fully relies on, like this part is from this part. And from the blue images is also taking this part. But now we want to focus on this part. So this part is the overlapping images. So in here, we try to put a sign like the weights to each and compute the weight sum of their intensities, so we can gradually decrease or increase like the distance. Because I mean, from 2 images, they might have a different like intensity, brightness and stuff. So by we actually put on weighting and stuff, then we can actually make it more smoothly, like the final result over there. Then there are actually 2 methods of blending depending on what kind of situation you want to solve it. So first is the multi-band or Laplacian pyramid blending. Pyramid blending. And the second one is gradient domain Poisson blending.
This OI in French is what? Yeah. Yeah, Poisson.
Okay,
Yeah.
Poisson
Yeah.
blending. So now first we start like how to do the multi-band or Laplacian pyramid blending. So it worked by first we have like two images, right? Different one. The apple and the orange. So we create we first try to break these images into half, and now you can get like this one if we just directly connect it. But we want to do the blending to make it smoothly, because if you actually see like this part, it's very disconnected. So we create a Gaussian pyramid by repeatedly blurring and downsampling the image from the sharp to a very like blurry. Then now we can compute like the Laplacian pyramid and represent the fine details or high frequency information. So in here, as you can see, if we actually put that, now we can have more smoother pyramid blending. Yeah, because the blurring helps to make it more combined.
Okay, the previous page. Please press the escape key. Yeah, and then choose this, and then make it italics because they are the variables. Yeah. So please choose from here to here.
This one?
Good. Yeah, no, starting from G. Starting from G. Yeah. Okay, italics.
Professor, sorry. My presentation is a free one. I cannot edit it in here.
Oh, so it's a PDF?
It's a PPT presentation, but the Microsoft needs a subscription, so I cannot edit it.
Oh, okay. I think the university offers a free PowerPoint for every student. You can use that one. Yeah.
Okay, sorry. Okay. So where are we going? Oh, okay. So finally we got like the smooth blending, right? Then how about the gradient domain of Poisson blending? So in here, there is actually two images, if you notice, but they have a different gradient or different like brightness. And in here, we want, after the image stitching, we want to try it to make it more smoothly by trying to adjust this gradient distance. Then how to do that is that it takes the gradient from the left side and also take the gradient on the right side, and then like stitch this gradient together, and after that we can get this part. And this technique is called as the gradient domain blending, and it also more advanced blending method compared to the previous one, the Poisson. So to make it more deep on how to do the gradient domain Poisson blending, so in here, if you see that the first images in second images, then the first images gradient that we want is being pasted on the here. So after that, we try to solve for the color image internal gradients, because you see, yeah, the difference of the gradients doesn't make it more smooth, like doesn't look natural. So now we need to try to match like the color boundary, and this way we can like transition it to more like naturally and seem becomes like more invisible, like yeah, that's basically this one. So to summarize, we choose like different technique of blending, depends of what we want to solve, right? So this is called as the scene selection. For example, if you have a static scene and the brightness difference is like 1 until 3, then you're gonna use the multi-blending. But if you have a large brightness difference or color tone difference, like the example of the previous one, then we can perform the local exposure first, and after that do the Poisson blending. And for the moving objects issue, we can first determine the seam of the graph cut to remove the ghosting. And after that, we can apply either the multiband or Poisson blending, depends on what you want. So the thing is, there's still issue. So the issue in blending is that if we stitch these images like sequentially from left to the right into a very complete panorama, this knot can perfect align because their position is not exactly the same. As you can see, there is like one above, one below, something like that. Their position is not the same. So we need to align them first. To align them, the simple solution is just to crop them and find the largest possible rectangle and just crop the images, and now we can get this part. However, if you notice, this sacrifice like some information, and this information is not being used. And another issue in the stitching, image stitching, even a very small errors can accumulate over time, and this lead to the drift. This is actually already being explained in the previous slide. In the section of 8.2. And when we stitch images in a loop, the first image should match the last image. However, if we look at the smiley face in here, it should be the same object of the smiley face, right? But it doesn't align together. And so that, how to do this is that we need a linear correction. Since we know that these two smiley face, this first in the first image and the end image is like the same, then we can just directly take this image and copy it directly in here. So we can compute their difference. For example, if their y difference is 100 and the total image width is 1000, then the drift can distribute it linearly, and this means we can just shifting 10 pixels per 100 pixels. After processing, the image may also appear slanted like this part, as you can see. But we can just solve this easily. Basically, just use like the crop solution, directly cut it if it's slanted. However, as I stated before also, if you crop, then you're gonna lose information. So is there any other methods to do that? Yes. And one of the approach is using the like hole filling, as you can see in that one, figure B. But in this part and in this part, this one is like have an unrealistic artifacts. And that's why another solution is just doing the warping of the images to transform this part into a rectangular one. And this is called as a local dewarping. So we slightly adjusted like the small region around, and overall the image will just look more natural compared to just to the whole filling. And we can get also the rectangular shape. So yeah, congratulations, we finally can apply everything that we have learned in this chapter, and we can generate like panoramic image and display it for the viewer as a visualization like this one. And for this part is like the format. So this part is like if you don't understand any term, like for example alignment, local stitching, global optimization, seamless blending, you can refer to the very last slide at 92, number 92. So yeah, that's all for the chapter 8. Thank you. Let's take a break before the research.
Yes. Yeah. I like the video. Yeah. Okay.
Okay, I think we can finish the class.
Okay. All right. That's all for today.